move this around a little bit. Now we can have maybe better visual dynamics, right? I actually put away this thing. So you guys have a chance to come in. We want to congratulate uh, our graduating class. And we want to thank all of our new students for coming in. Gracias a todos nuestros nuevos estudiantes. Felicidades a la clase que se me graduó. Pude compartir un momento muy especial con todos mis graduantes y sus familias, aunque el evento fue un poco breve porque estaba lloviendo, pero sí me puse un poquito emocional, le di la gracia. Ustedes son mi inspiración y la razón por qué yo hago todo. Hoy vamos a continuar con nuestro repaso de la clase de ingeniería y vamos a continuar. La mayoría de los nuevos estudiantes empezaron con los alumnos que se estaban graduando. Entonces, le abrimos la oportunidad de que participaran para que cuando comenzaran pudieran arrancar muy bien. Entonces, por el momento voy a utilizar mi plataforma portátil porque no quiero sobrecargar mi sistema, pero vinimos preparados. Vamos a ver cómo podemos ajustar el formato. Déjenme chequear, la batería está bien. Denme un segundito. Dios me lo bendiga a todos. Gracias por venir. Yo sé que a veces es difícil cuando uno tiene una familia o quizás las circunstancias no son las mejores, pero siempre hacemos el esfuerzo de estar aquí. Y si por cualquier razón ustedes no pueden atender una clase, siempre tienen todo grabado, etcétera. Algo que sí voy a hacer es apoderar el sonido. Vamos a buscar algo relajante. Espero que ustedes hagan lo mismo. Vamos a ir a... ¿Qué tengo por aquí? Bossa Nova. Ok. Vamos a comenzar con esto. Bajar esto un poco. Porque tengo que ajustar todo en Pro Tools. Aquí puedo controlar esto. Perfecto. Siempre, realmente me van a poner un comercial porque así funciona. Déjame asegurarme de que lo tengo en radio. Puedo comenzar todo de nuevo y tengo control aquí, ¿no? Que puedo ajustar aquí. Y puedo ajustar aquí también para tener un buen balance. Ok, so, otra cosa, vamos a terminar un poquito temprano por el día de hoy. Vamos a empezar. Oh, Dios mío, comerciales. Tú, ahí es que se dañan estas aplicaciones. Vamos a empezar con la aplicación Motivational Quotes. ¿Verdad? Ok, so aquí empezamos, ok. Vamos a ver si tengo, ok, quizá un formato poquito mejor aquí, ¿verdad? Vamos a trabajar con lo que Dios no ha dado, okay? So here's some inspirational quotes. Let's start the day like that. Imagine the best version of yourself and you will grow in that direction. Isn't that cool? Not a good way to start the day, right? Oh, representing, baby. Okay. Mm, okay. Now let's open up business management. Mm, we have 41 lessons on calculus. So let's begin with that. Okay. Okay. Introduction. Calculus is a classical branch of mathematics dealing with the study of functions. A function is essentially a rule for association, one of one or more input variables with an output value. For instance, we might be interested in relating a decision, say how much to produce, to the business outcome, say profit. We have seen that this is needed, for instance, to figure out the best mix of products, building a relationship, linking managerial levers, and the resulting outcome is essential in tackling any decision problem. In other cases, our aim is somewhat more instrumental. In statistical model building, we want to find a mathematical representation that yields the best fit between the empirically observed data and the predictions of the model. To accomplish this task, first, we need to choose a functional form dependent on some unknown parameters. And then we must choose another function expressing the lack of fit, which in turn is related to prediction errors. Empirical model building calls for the minimization of such lack of fit. In real life, we deal with functions of many variables, but in this chapter, we just deal with functions of one variable. For example, rules mapping one input value, x, to an output value, y, equals f parentheses x. We may introduce all of the required concepts in this simplified setting. Later, precisely at the end of the next chapter, we will generalize to functions of multiple variables. Given a function, the first task that comes to our mind is plotting in order to get an intuitive feeling for the relationship between x and y, and to analyze the sensitivity of the output to variations in the input. Typical questions are as follows. Number one, how will a slight variation in interest rates affect an investment decision? How will a change in unit cost of some raw material affect total profit from manufacturing a product? To deal with these important issues, we introduce a fundamental concept, the derivative of a function. The same concept is also essential in optimizing a function. An example, in finding decisions, maximizing profit, or minimizing costs. Studying the related issues, such as convexity and concavity of functions, paves the way for later dealing with optimization models. We will also hint at some other important concepts, such as sequences, series, and integrals, even though our treatment will be quite brief and limited to what is really essential to understand a few topics. A motivating example: economic order quantity. Before getting into formal details of calculus, it is essential to arm ourselves with some motivation for doing so. In management science, we often want to relate decisions to cost or profit. This is necessary in order to find an optimal decision yielding the best performance in some well specified sense. We should quote optimal because our decision is just optimal. Because our decision is just optimal with respect to our cost or profit model. It is often said that all models are wrong, but some are useful. Indeed, a model can be a quite rough representation of a possibly complicated and uncertain reality. There's something here. I don't know what it is, but we're going to continue. Okay. Let's go back from the beginning. Lecture number two, slash 41. A motivating example, economic order quantity. Before getting into formal details of calculus, it is essential to arm ourselves with some motivation for doing so. In management science, we often want to relate decisions to cost or profit. This is necessary in order to find an optimal decision yielding the best performance in some well specified sense. We should quote optimal because our decision is just optimal with respect to our cost and profit model. It is often said that all models are wrong, but some are useful. Indeed, a model can be a quite rough representation of a possibly complicated and uncertain reality. Still, it can be useful to sharpen our understanding and to find a good decision. We should never forget that a quantitative model is just a decision aid and not a magical oracle. A case in point is the economic order quantity EOQ model. This is a somewhat old style archetypal model for inventory management, relying on a lot of debatable assumptions. Yet it can have some value in practice and is a good way to show mathematical modeling and calculus in action. Imagine that you are in charge of managing the inventory of an item at a retail shop. Inventory is depleted at a rate dependent on demand, and every now and then you have to replenish inventory by issuing a purchase order to a supplier, or maybe a production order to your own manufacturing facility. To keep it simple, let us assume that demand is perfectly constant in time, and let D denote the demand rate. The demand rate is the demand per unit time, such as 10 items per day or 75 items per week. The specific time unit is not important, provided we are consistent in specifying all of the relevant data. Which kind of decisions are you supposed to make? Number one, actually, there are two decisions involved here. Number one, when to order. Number two, how much to order. The first decision, in an ideal world, is actually trivial. By ideal world, we mean a world in which there is no uncertainty involved. Number one, demand is perfectly predictable, even constant, under our assumptions. We also assume that demand is fluid in the sense that we approximate the discrete flow of items out of inventory, one piece at a time, as a continuous flow. Number two, the time it takes to get a shipment from the supplier is fixed and known. This time is known as lead time or time to delivery. In this setting, you should issue a replenishment order when inventory reaches a level of corresponding to demand during lead time. For instance, if time to delivery is 2 days and the demand rate is 10 items per day, it is easy to see that you should issue an order when your inventory level decreases to 20 items. Section 2. Doing so, you will receive the new stuff exactly when you run out of stock. Clearly, such magic does not happen in real life, but for our little example, we may ignore issues related to variability in time to deliver and timing of orders. Figure 2.1, time evolution of inventory levels in EOQ model. So let me just pull it up to the screen so you guys see what it looks like. Okay? Okay. As the second decision, since demand is constant, it is reasonable to assume that whenever you replenish, you always order the same amount. In example, your preferred order size. Let Q be the order size we choose. And without loss of generality, assume that we start with Q units on hand. The resulting inventory pattern will look like figure 2.1, where slash denotes the inventory level and T denotes time. We see that the inventory pattern is periodic as we issue an order every Q/D time units. For instance, if we demand or if the demand rate were 100 times or 100 items per week, and order size Q equals 300 would result in a replenishment order every 3 weeks. In practice, the inventory plot would be a stepwise function as we sell one item at a time and not fractions of items. Yet if demand volume is large enough, a continuous pattern like the one in the figure is a fair approximation. The case of sporadic demand for a niche product should be addressed by a different modeling approach. So, under our quite strong assumptions, we have just one decision to make: finding the right amount, Q, to order. In example, the economic order quantity, OEQ or EOQ. Indeed, this is a matter of compromise between conflicting needs. Number one, imagine that whenever you issue an order, a fixed charge, Section 3, is incurred. For instance, if your supplier ships a container, quite reasonably, the shipping charge will include a fixed component that does not depend on what and how much is transported. Hence, from this perspective, you would like to order a rather large amount whenever you replenish in order to spread the fixed ordering charge on as many items as possible. Put another way, the less orders are issued per year, the better. On the other hand, you would like to order just a few items quite often. Doing so is important when items such as fresh produce are perishable and their limited shelf life precludes stocking large amounts. Perishability should not be confused with a similar issue, obsolescence, which is typical of fashion products or items characterized by a fast pace of technological innovation, such as consumer electronics. Section 4. Even if you do not consider such issues, there is a good financial reason to keep inventories low. When you receive a shipment from your supplier, you pay her. And this means that you have tied up some liquid cash to your inventory. When you sell, you will get your money back plus a profit margin. But having too much liquidity immobilized there may be a bad idea. Apart from this opportunity, cost of capital, large on hand inventories also imply high insurance costs. Even worse, you may end up with a huge inventory of a slow moving item, lacking liquidity and precluding the purchase of items that are in demand unless you borrow money from a bank, incurring possibly high interest rates. Note that in our setting, we should not consider profit since we are assuming that we will satisfy all of the customers anyway. Hence, our problem is just satisfying demand at minimum cost. And this in turn requires spotting the right compromise between the two conflicting requirements above. How can we do that? Number one, there are three tasks that we should accomplish in sequence. Number one, we should make the relationship between the decision Q and the total cost explicit. To this aim, we may write down a function CTOT parenthesis Q, mapping order size Q into total cost. To be more precise, we will consider the average total cost per unit time. To fix ideas, we assume that our time unit is exactly 1 year. Number two, we should sketch a graph of the total cost function to see what impact our decisions have on average total cost per year. Number three, finally, we should find the best decision. In example, the optimal order size, Q star, so that the cost function attains its minimum. Task number 1, representing the total cost function. In order to express average total cost per unit time as a function of the order size Q, we should consider all of the factors contributing to the overall cost. The first one that comes to mind is purchase cost. If the unit item cost is C, measured in money per item, we have to pay CQ whenever we replenish. This variable cost per order must be translated in terms of cost per unit time. If we issue an order every Q/D years, parentheses, our time unit, then we will issue D/Q orders per year on the average. For instance, if demand rate is 1,200 items per year and the order size is Q equals 100, we will issue 12 orders per year. Hence, the contribution of purchasing to total cost is just the product of cost per order times average number of orders. Again, let me let you have a quick look so you guys can see that. That is the breakdown right there. On second thought, this is obvious. In order to satisfy total demand during 1 year, we have to order D items anyway. Whether in small or large batches, we notice immediately that this term does not depend on Q, as we are disregarding possible discounts based on ordered quantity, which would make the unit cost a function, C parenthesis Q, of the order size. Now let us consider the contribution to total cost from the fixed charge component. Whenever we order, we have to pay A, euros, dollars, Bitcoin, or whatever, precious metals. And we have already found that the average number of orders we issue per year is D/Q on the average. Then the contribution from the fixed ordering charge is C over OR equals A dot D over Q. Finally, we need the contribution due to inventory holding. This is a bit trickier, and we should clarify which kind of cost we are dealing with. If we keep one item in inventory for 1 year, we incur a cost. Let us denote this unit inventory holding cost by H. It is important to realize that the dimension of this unit inventory holding costs are money per item per unit time. In a sense, this is a twice unit cost with respect to volume and with respect to time. There are a few ways to figure out the contribution from holding costs, and all of them require a careful look at figure 2.1. There we see that the inventory level ranges between 0 and Q and changes according to a smooth and constant rate. The pattern is repeated every Q/D time units. Consider an order for Q items. A good question is, how much time does an item of that shipment spend sitting in our warehouse? Number 1. Actually, the first item that gets issued from inventory waits no time at all. In our abstract model, it is placed into the warehouse when we receive the shipment, but it is immediately sold. The less lucky item is the last one, as it will wait Q/D time units. On average, the waiting time for an item will just be the average between the two limit values, 0 and Q/D, in example Q/parentheses 2D. Since there are D items going through the inventory each year, the contribution to total cost from inventory holding is C over IN equals H dot D dot Q over 2D, which is equal H Q over 2. Let me show you that illustration. That's what it looks like right there. Please take note. As an alternative way to obtain the same result, we may consider the average inventory level. Since the inventory level ranges between Q to 0 and changes uniformly in time, its average is Q/2. Multiplying average inventory level by H yields the result above. This alternative view has the advantage of being generalized at any inventory pattern, not necessarily a constant and uniform one. Now we are ready to put all of it together. The average total cost per year as a function of Q is as follows. C over TOT parentheses Q equals C over IN plus C over OR plus C over PU equals H Q over 2 plus AD over Q plus CD. Please look at the illustration. They are not the same, okay? They are similar in components of each other, but this is calculus, so they're not one and the same. They're elements of the same group or categories. One thing is immediately clear. The purchase cost component is constant and does not play any role in determining the optimal order size. If you have any difficulty in seeing this, please have another look at figure 1.2. Once again, let's have a look. They look the same, but they're not the same. This is a different expression. As we see, a function f parentheses dot is essentially a rule mapping an independent variable, q in our case, into a value y equals f parentheses q of a dependent variable. Notations like f parentheses dot or f are used to emphasize the difference between the function itself, a rule to map variables to values, and the output value, f parentheses q, taken for an input value, q parentheses a specific numerical value. So here in the bottom, it tells you f parentheses dot is essentially a rule mapping. So please read that right there in the bottom. So it's an independent variable, q in our case, into a value y equals f parentheses q of a dependent variable. Notations like f dot parentheses or f are used to emphasize the difference between the function itself, a rule to map variables to values. So variables to values is one all by itself, and the output value f over q taken for an input value q over a specific numerical value, which could just be a variable for business. Task number 2. Plotting the total cost function. Having figured out a relationship between the order size and the average total cost per year, it would be useful to plot the function in order to see the effect of Q and to figure out a good decision. There are plenty of powerful software packages that, given a range of the independent variable Q, compute the corresponding values F parentheses Q and display the result graphically. This is certainly quite useful, but we should also be able to figure out some basic properties of the function by just looking at its expression. There are a few reasons justifying the need for this ability. Number one, it is helpful when evaluating the function numerically is difficult or prone to numerical errors. Number two, it is often the case that a function cannot be evaluated for some values of the independent variable, but a piece of software will not help you in understanding what is going wrong. In more complicated settings, we may not just rely on brute computational force to see this. Imagine plotting a function dependent on more than two independent variables. Last but not least, this exercise helps in honing skills and improving understanding. Let's have a quick look. This is what it's going to look like. So let's read along. Figure 2.2, inventory holding and fixed ordering. Charge components in the EOQ model. In general, plotting a function can be difficult, but it is fairly easy in the case of EOQ, cost model, disregarding the constant term. The essential form of the total cost function is C over TOT parentheses Q equals AQ plus B over Q, where A equals H over 2 and B equals AD. From our high school background, we should immediately see that this function is just the sum of a straight line, AQ, going through the origin and the hyperbola B over Q. See figure 2.2. To get a rough picture of the function, let us consider the two extreme cases. Number one, when Q is very small, the linear component AQ is small too, but the nonlinear component B forward slash Q gets larger and larger. In fact, for a very small order size, the inventory holding cost component goes to zero, but the fixed charge component increases without limits because we are spreading the fixed ordering charge over a tiny number of items. We cannot evaluate C over TOT parentheses Q for Q equals 0, since we cannot divide by 0, but we can write lim Q minus plus C over TOT parentheses Q equals plus 0, 0 in continuation. This notation has a precise mathematical meaning, but the informal interpretation is that the limit of the total cost goes to plus infinity when Q tends to 0. Notations like lim equals Q over 0 plus or lim Q minus 0. Are used to indicate that Q goes to 0 while staying on the positive side. A negative order size makes no sense. We say that Q goes to 0 from the right or from above. So in the range of small order sizes, the nonlinear component prevails, and the function looks like a hyperbola. Number two, when Q is very large, the linear component AQ is large too, as large holding costs are incurred. On the other side of the coin, the nonlinear component B over Q goes to 0. Since the fixed charge component is spread on a huge amount of items in this range of large order sizes, it is the linear component that prevails, and the function looks like a straight line. In this case, the limit of the cost function goes to infinity. Lim to the right Q plus infinity equals C over TOT parentheses Q equals plus infinity. The result of these observations is a sketch like that in figure 2.2. Indeed, we see that there are very bad decisions corresponding to very large or very small order sizes, and some good ones, for which cost is much lower. Now we have to find the optimal compromise. Task 3. Finding the best decision. In plotting the function, we have ignored the purchase cost component, CD, which is constant and would just push the graph up a bit. This is not relevant to us, since what we are interested in is finding an order size. Q star, minimizing total cost. Indeed, since the function goes to infinity for very small and very large order sizes, we would expect that somewhere in between there is an optimal order size, the EOQ. One possible way of finding the EOQ is by trial and error. An example, by calculating the cost of several input values and spotting the best choice. Unfortunately, this brute force approach is time-consuming, not quite informative, and not feasible in more complicated cases. We will learn a more straightforward way to spot a minimum cost or maximum profit solution based on the concept of function derivative. For now, we can observe that the minimum cost solution is a point where the tangent line to the function graph is horizontal. This is illustrated in figure 2.3 parentheses A. 3 tangent lines are shown, and indeed the minimum cost solution is where the tangent line is horizontal. It seems that if the tangent line corresponding to an order size is not horizontal, we may find an improvement by moving to the left or to the right. Actually, this reasoning is not 100% correct, and this solution needs some refinement. Still, using concepts explained later along these lines, it will be easy to see that the optimal order size, according to the EOQ model, is Q star equals 2AD over H 2.1. Figure 2.3 parentheses A. Tangent lines to the total cost function, and B, the optimal cost in the EOQ model for varying demand rate D. If we plug the optimal order size into the total cost function, we get the average cost per year for the optimal solution as a function to the demand rate D. C star over TOT parentheses D equals average 2AHD plus coefficient of drag. This function is plotted in 2.3b, and it's interesting to note its shape. As expected, it is an increasing function of the demand rate. This is no surprise after all. The larger the demand that must be satisfied, the larger the incurred cost. What is not that obvious is that the rate at which the function increases is decreasing. To see this, imagine drawing tangent lines at different points on that graph. The slopes of the tangent lines are decreasing with respect to demand rate D. This is a typical behavior of cost functions, exhibiting economies of scale. We will learn later that a function like that is a concave function. A little background. As we have already pointed out, the reader is assumed to be equipped with a basic mathematical background about sets as well as integer and real numbers. Sets as well as in this section, we briefly recall a few basic concepts for convenience. Real versus integer numbers. If we order cars from a car manufacturer, we cannot order 10.56986 cars. We may order either 10 or 11 cars. But any value in between makes no sense. It should be intuitively clear what we mean by an integer number. Integer numbers are used to measure variables that have an intrinsically discrete nature. A real number is a number with some, possibly infinite, decimal parts. Real numbers are not that obvious to characterize formally. But intuitively, a real variable is used to measure something that has an intrinsically continuous or fluid nature. In the following, we denote the set of real numbers by and the set of integer numbers by z, so r over z. If we are just interested in non-negative numbers, we use notations r plus and z plus. The real timeline. Real numbers can be represented on a real line as illustrated in figure 2.4, ranging from minus infinity to plus infinity. Given any pair of real numbers on the real line, you can always find a real number between them. For instance, given x1 equals 2.3982 or x2 equals 2.3983, we can actually find infinitely many real numbers between them. One example is x equals 2.3982133. The set of real numbers is dense, whereas the set of integer numbers is not. There is no integer number between 10 and 11. Intervals on the real line. Inequities like a greater than x greater than b, where a and b are arbitrary real numbers such that a is greater than b, define intervals on the real line. The inequality above defines an interval that includes its extreme points. In such a case, we use the notation box A /B to denote the interval, and we speak of a closed interval. On the contrary, inequalities A less than X less than B define the open interval, parentheses A/B. For instance, the point X equals 10 belongs to the closed interval box 0/10. but does not belong to open interval 0/10, parentheses. We may also consider open closed intervals like box A parentheses B, corresponding to inequalities as A less than X less than B, or A parentheses A box B, corresponding to inequalities A is less than X less than B. If both A and B are finite, we have a bounded interval. We may also consider unbounded intervals by extending the real line to include plus infinity, over infinity. Examples of unbounded intervals are: number one, negative to infinity, parentheses, box A, corresponding to X is less than A. Number two, box A plus infinity, parentheses, corresponding to X is greater than A. And number three, negative infinity plus infinity, parentheses, which is the whole real line. Note that there are infinite integer numbers in Z, as well as infinite real numbers in R. However, we cannot say that the two sets have the same order of infinity. To see this informally, note that there are infinite real numbers even in a bounded interval like box 0, box 1. To get an infinite set of integer numbers, we have to consider an unbounded interval. When we have an infinite collection of items that can be counted, an example can be placed in correspondence with the set of integer numbers, we speak of a countably infinite set. For instance, a sequence of arbitrary real numbers x over k for k equals 1, 2, 3 is an infinite sequence, but it includes less points than the bounded interval box 0/1 box. More generally, we speak of the numerable or countable sets, including also finite collections of elements. The sum notation. Consider an expression like x1 plus x2 plus x3 plus x4. We will meet similar expressions quite often in the book, and a nice shorthand notation for this expression is which should be read as the sum of x subscript I for I ranging from 1 to 4. Sometimes the sum limits can be symbolic, as in, we may even consider an infinite sum like. Here are your two examples in the bottom. In this case, we should wonder whether the expression makes sense, since summing an infinite number of terms may result in a sum going to infinity. A thorough study of the involved issues requires the theory of mathematical series. In section 2.12, we deal with a few examples that are most relevant in applications. In some cases, we might wish to skip values corresponding to some subscript. Finally, when variables have two subscripts, we may consider double sums. In this example, we also see that the order of the two sums is irrelevant and they may be swapped. we will always take for granted that this is the case, even though some care should be taken with infinite sums. When sum limits are irrelevant, we may use streamlined notations like the latter notation comes in handy when we want to exclude terms of the form x11, x22, x23, or x33, etc. Permutations and combinations. Many practical problems involve permutations and combinations of objects. A first question is, given a collection of n objects, in how many ways can we permute them? For instance, let us consider the set A, B, and C. Since the set is quite small, we can enumerate all of the possible permutations systematically. First, we consider permutations beginning with A. We can form two such permutations, parentheses A, B, C, and parentheses A, C, B. Then, considering permutations starting with B, we have B, A, C, parentheses, and B, C, A, parentheses. And by the same token, we have C, A, B, parentheses, C, B, A, parentheses, beginning with C. Hence, there are 6 possible permutations of 3 objects. But what can we say in general for n objects? Again, let us be systematic in our enumeration of permutations. Number 1, when we choose the first item in the sequence, we have n possibilities. Number 2, when we choose the second item, we have n minus 1 possibilities, since one object has already been used to fill the first slot. Number 3, when we choose the third item, we have n minus 2 possibilities, since 2 objects have already been used to fill the first and second slots. Number 4, when we have only 2 items to go, we can choose among 2. Number 5, when we have 1 item left, there is just one possible choice. Hence, the total number of permutations of an object is n times parentheses n minus 1 times parentheses n minus 2 times parentheses n minus 3 x dot 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 x2 x1. The kind of product above is so common that it has been given a name. Definition 2.1 factorial. Given a positive integer number n, the factorial of n denoted by n is defined as n equals nx parentheses n minus 1 times n minus 2 times n minus 3 x dot 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 x2 x1. The factorial can also be defined recursively as n equals nx parentheses n minus 1. And by convention, we set 0 equals 1. A noteworthy feature of the factorial function is that it grows very quickly with n. 3 equals 6, 5 equals 120, 10 equals 3,628,800. This process is known as combinatorial explosion and has practical implications. The word for today is combinatorial. Example 2.1. Imagine that you are a traveling salesperson. you live in a city and your task is to visit customers living in other cities and then come back home. Let n be the number of cities you have to visit, not including yours. All of them must be visited exactly once. Arguably, you would like to follow the shortest route in your tour. Geographic information systems can provide you with distances dij or d over ij between any pair of cities, parentheses I forward slash j, where I, infinity j, and the indices range over the set 0, 1, 2, n. Say that 0 is your city. How can we find the optimal tour? One obvious idea is that since there must be a finite number of tours, we could just enumerate all of them and pick up the shortest one. Using a fast computer, this should be no big deal. But how many tours must be evaluated? We have n plus 1 cities to visit. There are parentheses n plus 1 permutations of them, but actually only n are really different. One way of seeing this is observing that the first city is your home and is fixed. An alternative view is that we do have n plus 1 parentheses, different tours, since there are n plus 1 possible starting points. But the total length is not really influenced by the starting city, as the tour is a closed cycle. Hence, the number of different tours in terms of total length is parentheses n plus 1 forward slash parentheses n plus 1 equals n. The problem is further simplified if we assume symmetric distances. In example, d over ij equals dji dot. In fact, there is little difference in terms of mileage between traveling from Boston to New York or from New York to Boston. This may not apply on a smaller scale within a city. One-way streets make distances asymmetric. If we assume symmetry, we have two equivalent ways of traveling along each tour. You may visualize them as a clockwise and a counterclockwise tour. Hence, the total number of different tours is n forward slash 2 dot. Now say that you have to visit 25 customers. Using any pocket calculator, we obtain 25 wave 1.55112 by 10.25, or 10 squared to the 25th power. Some difficult number to read. It means that there are about 15.512 millions of billions of possible permutations of 25 cities. Luckily, we must only consider half of those, and we also have a very fast computer. Say that we are able to generate and evaluate 1 billion permutations, in example 10 to the 9th power per second. Since there are 3,600 seconds per hour, 24 hours per day, and 365 days per year, we will get the optimal tour after 1.5511 times 10 to the 25th power over 2 times 10 to the 9th power by 3600 by 24 by 365 equals 245,928,621.95 years. Patience is indeed a virtue, but you need a solution, not your many times grand minus nephews. Luckily, there are much smarter ways to find the optimal solution using some good mathematics. Now, let us consider a slightly different combinatorial problem. We have n items and we want to select a combination of r of them. To see a practical setting in which a combination of items must be selected, imagine a batch of n manufactured parts from which a random sample of our items is drawn for a quality check. How many combinations of our items out of n can we form? Number one. One way to look at the task is the following. We take any permutation of n items and we know that there are n possible permutations. Number two, then we select the first r items and we include them into our combination, leaving the remaining n minus r items outside. However, we are not really interested in the order of the r items. All of their r permutations correspond to the same combination, and the same applies for the parentheses n minus r permutations of the objects that we do not include in the combination. Hence, there are n over r parentheses n minus r combinations of r items out of n, as this quantity is quite common too. It has earned a specific name. Definition 2.2, binomial coefficient. Given positive integer numbers n and r is greater or less than n, the binomial coefficient is defined as parentheses n over r equals infinity n over r over parentheses n minus r. Example 2.2. Consider n equals 4 objects. How many combinations of two items can we form? Using binomial coefficients, we find 4 over 2 parentheses equals 4 over 2 parentheses 4 minus 2 equals 4 times 3 times 2 over 2 times 2 equals 6. Indeed, in soccer championships, groups of 4 teams are formed and 6 matches between all of them played. Note that in this case, the order of the 2 teams in defining a match is inconsequential, as there are no return matches, meaning single elimination. To see where the name binomial comes from, we recall the binomial expansion formula, figure 2.3. Parentheses a plus b squared equals a squared plus 2ab plus b squared equals a plus b to the third power is equal to a to the third power plus 3a to the second power, b plus 3ab to the second power plus b to the third power. Let us work them out using the binomial expansion formula. For the first case, we have a plus b squared equals 2 over k, which equals 0, parentheses n over n minus k, a to the n power minus k, b to the k power equals 2 parentheses a to the second power, b to the 0 power plus 2, 1, parentheses, a to the first power, b to the first power plus 2 over 0, parentheses, a to the 0 power, b to the second power. 2 over 2 times 0, a to the second power plus 2 over 1 times 1, ab plus 2 over 0 times 2b squared, or a to the second power, 2ab plus b to the second power as well. Where we see the usefulness of setting 0 equals 1 in definition 2.1, the second case is also easy to check by observing that 3 over 2 parentheses equals 3 over 2 times 1 equals 6 over 2, which equals 3. In practice, when computing a binomial coefficient, care must be taken as large numbers can result in overflow errors on a computer. Chapter 5. A good way to simplify the calculation is to note that. So let's take an example, because remember, we're going to be working on coefficient of drag, and this is how we're going to determine it. As well as on the exams, I'm always going to ask you guys to show your work. Functions. Functions are rules that map input values to output values in a well-determined way. They come in many guises, depending on what is mapped on what. Generally, a function is specified as f dot d minus I, where d is the domain of the function. In example, the set of possible input values on which the function is defined, and / is the image or range of the function. In example, the set of values that we obtain by applying the function to each x in the domain D. In this book, we are essentially interested in numerical functions like f parentheses x equals x plus 2. This is an example of a single variable function mapping real numbers into real numbers. Formally, this is denoted by f dot dot r minus r. Sometimes we have to restrict the domain to integer values. Consider, for instance, a function mapping the number of electric motors we use or we buy to the purchasing cost. Obviously, we can only buy a non-negative and integer number of motors. Hence, we should specify a function g equals z plus greater than r plus, where, as we said, z plus and r plus denote the set of non-negative integer and non-negative real numbers, respectively. Segment 6. If the number of items we buy is large, it may be convenient to express a function g equals r plus greater than r plus, which is a sensible approximation and may be easier to work with from a computational perspective, as we shall see. In other cases, the domain D is restricted because of conditions that ensure the proper definition of the function. Example 2.4, consider the function f parentheses x equals alternative 1 minus x to the second power. The square root function is defined on non-negative real numbers. Section 7. Hence, the domain of f is restricted by the condition. The domain restriction is reflected by denoting the function as f box negative 1, 1 greater than r plus. In the case of g parentheses x equals 1 / x, we have g equals r / box 0 equals r / box 0, where we use a / b to denote set difference. In example, the set consisting of elements of A that are not elements of B. In fact, function g is not defined for x equals 0, and there is no solution to the equation 1/x equals 0, as the function tends to zero out for x greater than plus infinity over, but it is never exactly 0. Hence, both domain and range of G are the set of real numbers minus the singleton, parentheses 0, square root. The domain of G could also be denoted by parentheses x infinity r over x infinity 0. Once again, think about carbon fiber composites when we're weaving things together, strength, durability, how brittle it is, maybe even reinforcements, to give you an example. So we'll go into carbon fiber a little bit more because we're going to focus on coefficient of drag, how something is slippery and moves through the air. When we're designing and engineering, developing a high-performance vehicle, we need to be able to work with the air really, really well. Aerodynamics. Figure 2.5, surface plot for the function of example 2.5. We also use functions with multiple input values, such as functions f parentheses x, y. Here, the domain is the set of pairs of real numbers, parentheses x, y, denoted as the Cartesian product. R by R equals R to the second power. We defer a study of multivariable functions. Even the very basic tasks of plotting a multivariable function has no obvious solution, as shown in the example below. Example 2.5, plotting functions of multiple variables. Drawing the graph of a single variable function is, at least conceptually, a straightforward task. The case of multiple variables is not that easy, and there are different ways of representing them. Since we are just able to draw in 3 dimensions, we can only draw a surface corresponding to a function of 2 variables. For instance, the surface plot corresponding to function. So we want to design something where every single component is fully functional. If it has a vent, if it's to create downforce or lift, it has to be designed for that. So here's another example, illustration 2.5. This is where you will put your inputs. So when we do X, Y, Z axes, this is where we're building from. Illustrated in figure 2.5, the surface plot is obtained by drawing points in 3 dimensions where the vertical coordinate z is associated with function values z equals f parentheses xy. So the length, the width, the height divided by the weight, the power, and the wheelbase. And then combining that with coefficient of drag versus the competition so that the competition can be fair. Another useful plotting tool is the contour plot, the shape, right? Figure 2.6 shows the contour plot for the function above. This is a 2-dimensional plot displaying a set of level curves. A level curve consists of points on the plane, parentheses x, y. So normally we would do length by wheelbase, such that the function value is consistent or constant on the curve. There is a level curve for each value of the function. More formally, to draw a set of level curves, we fix a set of function values, z1, z2, z3, and plot curves defined by equations. So for example, performance vehicles can be in competition based on the liters, the class that it's in, the wheelbase, the overall length. So there are variables there for competition. So if you know your design and you know your target goal, specific competition, you can modify it based on those dynamics to be able to establish the airflow and the way that you want to move through the air. Because the vehicle can only do so much. Driver input is very important. So here's a figure here as an example. Again, when we're doing composites, when you're talking about stealth technology using, carbon fiber and things of that nature, this is what you're dealing with here. It could be the spectrum of aerodynamics. It could be a radar cross-section. Figure 2.6 contour plot for the function of example 2.5. Sometimes level curves may provide us with a clearer view of how a function behaves. From the example, we can immediately appreciate the limitations in our ability to see a function of multiple variables. This is why we need to develop tools that are useful in characterizing functions of many variables, even though we are not able to visualize them. These tools are also the foundations of numerical methods to solve complicated equations and to find optimal sets of decisions when many of them are involved. Luckily, we may build the intuition and the essential concepts that we need by dealing with the single variable case. In the reminder of this section, we illustrate the most common function classes, limiting our attention to those that are more relevant in a business setting. Linear functions. A linear affine function has the following general form: f parentheses x equals mx plus q, 2.4. Figure 2.7 shows a few linear functions. Strictly speaking, only the first function is linear. A function f is linear if the following condition holds. Figure 2.7 graphs of linear affine functions. For arbitrary numbers, ai and xi, I equals 1, 2. However, this holds only when the coefficient q in 2.4 is 0. To see this, note that for a generic linear affine function, whereas equating the two expressions leads to q equals 0. Nevertheless, we will often use the term linear in a loose sense, referring to linear affine functions, since coefficient q is the value of f when x equals 0. It represents the value of coordinate y at which the graph crosses the vertical axes. In fact, coefficient q is called the intercept, whereas coefficient m represents the slope of the linear function. The concept of slope is linked to the increment ratio of a function. Definition 2.3 increment ratio. Given a function f and 2 points xa and xb, such that xa is less than xb, or x over b, the increment ratio of f over those 2 points is defined as the increment ratio is the average rate at which the function increases or decreases. If the ratio is negative over the interval box x over a, x over b box. For a linear function, the increment ratio is, this is always the same for any pair of points. Indeed, a linear function is characterized by the fact that its slope is constant and tells us by how much the function changes for a unit change in the independent variable. The reader is invited to check the slopes of linear functions. So think about fluid dynamics. The way that the air interacts with the shape determines everything else because that's where it begins, the direction that the vehicle or the object is moving in. The reason why we use aircraft as an example is because of the composite technology, is because of all the systems integrated into the fighter jet or the aircraft. Therefore, we implement all of that in all of our unique designs. We may specify a particular line by giving its slope, m, and its intercept, q, i.e., the vertical coordinate of the point, parentheses 0, q, at which it crosses the vertical axis. This is your radar cross points for military designs. Alternatively, we can specify a line by giving its slope and one point, parentheses x, 0, y, 0, through which the function passes. This line is represented by the equation. Figure 2.8 graphs of polynomial functions. Y minus y over 0 equals m parentheses x minus x over 0, or y equals y over 0 plus m parentheses x minus x over 0, 2.5. So what do stealth aircraft that are, of the newer generation, what do they have in common? They're trying to reduce their radar signature, right? Right. Now, let's go back really quick. Let me see. Complexity data. Okay. Let's go to quantitative methods. Should we bother? Let's do our introduction because we're going to be basically working on this. Introduction. If you are reading this, chances are that you are on your way to becoming a manager. Or maybe you are striving to become a better one. It may also be the case that the very word manager sounds dreadful to you and conjures up images of unjustified bonuses. Yet you might be interested in how good management decisions should be made or supported in both the private and public sectors. Whatever your personal plan and taste, what makes a good manager or a good management decision? The requirements for a career in management make a quite long list, including interpersonal communication skills, intuition, human resource management, accounting, finance, operations management, and whatnot. Maybe if you look down the list of courses offered within master's programs in the sector, you will find quantitative methods, QMs. Often students consider this a rather boring, definitely hard, maybe moderately useful subject. I am sure that a few of my past students would agree that the greatest pleasure they got from such a course was just passing the exam and forgetting about it. Not all students, but it's a good way to start. So let me give you guys a quick overview of everything that we're going to be doing for this new winter semester. So we have quantitative methods, we have calculus, we have linear algebra, then we have elementary probability and statistics, where we have descriptive statistics, probability theories, discrete random variables, continuous random variables, dependence correlation, inferential statistics, simple linear regression, time series models, as well as models for decision making. We're going to do deterministic decision models, decision making on the risk, multiple decision makers that are subjective. And we're going to finish with advanced statistical modeling, introduction to multivariate analysis, advanced regression models, and dealing with complexity data. So we can shut this down. This has been amazing. Let me see what else I got for you guys here. Give me one quick second. Let me just check these apps. And we're going to go directly into the fun part. We'll be starting with the F-22 Raptor, and then we're going to go before and after, because there are talks through the grapevine. There may be a 6th, 7th generation fighter coming into play. We're going to go over the millionaire mindset, the self-made billionaire effect, 21 Secrets of Self-Made Millionaires by Brian Tracy. Of course, we got to do that. The Art of Strategy. We're going to do How I Made It, and we're going to do Secret Millionaire Clubs. Warren Buffett's 26 Secrets to Success. Let's start with that. Let's open that up. Again, we're going to go to the fun part. Let's just have a basic introduction. Shout out to Mr. Warren Buffett. In my book, in my magazine articles, I have Warren Buffett as Cyclops from the X-Men. I wrote a whole book about it. Okay. Let me see. Oh, this one has animation. Oh, man. For my younger students, they're going to love this. Here's one of the many secrets. It does have an illustration. Let me show it to you guys. So this is going to help you guys tremendously. Look at Mr. Warren Buffett right there. You heard me? All right. And here is secret number 1. Don't be afraid to make mistakes. Secret number 1. Try to learn from your mistakes. Better yet, learn from the mistakes of others. Hi again. I'm glad you want to learn more about Secret Millionaires Club. In fact, the first lesson is all about learning. When you own a business or manage a company, the last thing you want to do is make a mistake. You can lose customers and lose money by making too many mistakes. But sometimes slip-ups happen, and a successful business manager learns from his or her mistakes. It's the same thing in life. Learn from your mistakes. Better yet, learn from the mistakes of others. So that's just to give you guys a quick sampler there. What else we got for you guys? We have business startup, right? So let's do the introduction on business startup. Chapter 1, introduction. Why start a business? Tip number 1. I built a conglomerate and emerged the richest black man in the world in 2008, but it didn't happen overnight. It took me 30 years to get to where I am today. Youths of today aspire to be like me, but they want to achieve it overnight. It's not going to work. To build a successful business, you must start small and dream big. In the journey of entrepreneurship, tenacity of purpose is supreme. Aliko Dangote, businessman and entrepreneur. I could totally relate to this. 30 years in the music industry, probably close to 20 years in technology. And this is still day 1. I made a commitment to you guys. This is why you guys inspire me. We do this every day. So let's rock and roll. These principles are documented to give you, the reader, an insight into how everyday business can be conducted to keep your business flourishing. This is a way of bringing basic business information to your fingertips. According to research, majority of millionaires and billionaires are self-made and have made it through creating or being part of a business. If you have already decided that you want to start a business of that one thing you are very passionate about, then consider the fact that with starting this business, you need to understand that businesses take a lot of commitment. Number 1, dedication. Number 2, hard work. Number 3, and constant evaluation. Number 4, in order to flourish. Do not expect to get financially wealthy overnight. Below are a few reasons to start a business. Let's just go over number 1 and 2. Reach your dreams. If you have always wanted to be wildly successful, starting your own business could be a great start. Number 2, leave an inheritance. Pass the business down to your children and grandchildren. Number 3, abundance of resources. With the dominance of the internet, it's easier than ever to find resources you need, including loans, grants, mentors, and even startup capital. Number 4, there's nothing stopping you. What's really keeping you from being an entrepreneur? Of course, there are risks, but there's nothing forcing you not to take them. And number 5, make the world a better place. This may seem like an unrealistic goal for you right now, but your business really can make the world a better place. Then it goes into the benefits of owning a business. Again, this is just an example. So we're going to keep going because I built this curriculum over time. Let's go to, oh, wait a minute. Tell me I had this. Okay. Okay, this one we have to get back to. Okay, this is different. We have different templates for you guys to work on your business plans, but let us finish with the F-22, baby. Thank you. Thank you very much. F-22 Raptor. Now, you guys know this is my stuff right here. All right. Lockheed Martin F-22 Raptor. Why? Why are we choosing this aircraft? Because it is the basis of the actual design for the J Phoenix prototype, which I am the lead designer. And you guys get to be my engineers, my young apprentices. So here we go. Make sure I open all this up. And we could do the time. That's all. All right. Ready? Okay. Here we go. Lockheed Martin F-22 Raptor. The Lockheed Martin Boeing F-22 Raptor is an American twin-engine, all-weather, supersonic stealth fighter aircraft. As a product of the United States Air Force's Advanced Tactical Fighter Program, ATF, the aircraft was designed as an air superiority fighter, but also incorporates ground attack, electronic warfare, and signals intelligence capabilities. The prime contractor, Lockheed Martin, built most of the F-22 airframe and weapons systems and conducted final assembly, while program partner Boeing provided the wings, aft fuselage, avionics integration, and training systems. So you guys have all your chapters there defined. We're going to define what is a supersonic stealth fighter aircraft. We're going to talk about the United States Air Force, of course. We're going to talk about the Advanced Tactical Fighter Program. We're going to define what is an air superiority fighter. We're going to break down the difference between ground attack and electronic warfare and signals intelligence capabilities. We're going to go into Lockheed Martin. We're going to talk about Boeing. And we're going to talk about the avionics. So get ready, because this semester is going to be better than my class that just graduated. I love you guys. I miss you already. Right now, I would have been getting a text. Can you please send us the link? No, you need to be in class already. I used to always give them, before the exams, 2 minutes to walk in there. All right. So where are we? Where are we? Okay. Let's continue. First flown in 1997, the F-22 descended from the Lockheed YF-22 and was variously designated F-22 and FA-22 before formally entered service in December 2005 as the F-22A. Although the United States Air Force, USAF, had originally planned to buy a total of 750 ATFs to replace its F-15 Eagles, it later scaled down to 381, and the program was ultimately cut to 195 aircraft, 187 of them operational models, in 2009 due to political opposition from high costs, a lack of air-to-air missions at the time of production, and the development of the more affordable and versatile F-35. The last aircraft was delivered in 2012. So we're going to talk about F-15. We're going to talk about F-35, which is the active, what we're using, because of course it's a little more affordable. But we cannot go into the F-15 without going to the Phantom, without going to the F-14 Tomcat. We're going to talk about the F-18 Hornet. We're going to talk about the F-16 Striking Eagle, and we'll make our way back to the F-22. It's like when you talk about like the McLaren F1, I got to go all the way back to the 80s, then all the way back to today, and then back to it. And I get to do that with cars like the XA220, the EB110 GT, the Ferrari F50, etc. And of course, the talk of the town is 959, the Diablo F40, but there's a reason those cars had the impact that they did. But wait till we get to the Japanese counterparts. You already know. For the graduating class, I put that on the simulator, and it's crazy. Look how we chose the 33 as the perfect frame between the 32 and the 34. And two of my best childhood friends, these guys are my brothers. They're brothers, right? One favors the 32, one favors the 34, and I'm right dab in the middle. I'm the engineer, the designer, like, no, 33 is the best frame. The F-22 is a critical component to the U.S. Air Force current high-end tactical air power. So shout out to you, Morpheus. Shout out to you, C4. While it had a protracted development and initial operational difficulties, the aircraft became the service's leading platform for air-to-air missions against peer adversaries. Although designed for counter-air operations, the F-22 has also performed strike and electronic surveillance, including missions in the Middle East against the Islamic State and Assad-aligned forces. The F-22 is planned to remain a cornerstone of the United States Air Force fighter fleet until its succession by the crewed next-generation air dominance fighter. So we'll go into its development and things like that. So just as an example, what new vehicle can we add? I think we're going to go RX-7. Let's go to FD3S. And why not? We did what do you call that? We did an exclusive on every other model. We didn't go into full details for the 33, but obviously it's a new semester, so we're definitely going to do it. But this is just to pay homage, to put us in the right direction. We're going to go over the rotary engines, the technology. Most engines are like 40 parts or 40 moving parts. But let's just do our introduction on the FD3S, which we're going to start different. This semester, we're going to start with the JDM cars, and then we'll go back to all the previous design and engineering studies. The Mazda RX-7 is a front-engine, rear-wheel drive, rotary engine-powered sports car that was manufactured and marketed by Mazda from 1978 until 2002 across 3 generations, all of which made use of a compact, lightweight Wanko rotary engine. 94 RX-7 R2 FD3S. So let's fast forward to the 3rd gen, because that is where we need to be. 3rd generation, quick facts overview. Okay. Also known as the Affinity RX-7 from 91 to 97. Production was from 91 to 02. 68,589 models were built. And in America, North America, it was only released from 93 to 95, so 2 years. Designer Wu Huangqin, Tam Matano, Yoichi Sato, which is the chief engineer. Body and chassis two-door coupe powertrain, 1308 cc, 13B REW, twin turbo, twin rotor. Transmissions were a 5-speed manual or a 4-speed automatic. Let's talk about dimensions. So this is our X, Y, Z, and W axes. Wheelbase, 2,446 millimeters, 96.3 inches. Length, 4,285 millimeters, 168.7 inches. Width is 1,760 millimeters, 69.3 inches, and the height is 1,230 millimeters, 48.4 inches. Curb weight is 1,218 to 1,340 kilograms, which translates to 2,685 pounds to about 2,954 pounds. To give you an example, cars like the 5th generation Corvette and the 6th generation Corvette come in at under 3,000 pounds as well. And of course, they have between 350 and 430 horsepower. Some models have as much as 505 in the Z06, and the ZR1 is over 640, 630, 640 horsepower. They have a picture here of the winning concept design for the FD RX-7 designed by Wu Huangqin at Mazda's Design Center in Irvine, California. And they have a rear view. Here we go. The third generation RX-7, sometimes referred to as FD, chassis code FD3S for Japan, JM1FD for the North America market, featured an updated body design announced in October 1991. Production began later that month before going on sale in December in the domestic Japanese market. Left-hand drive export production began shortly after. The 13B REW engine was the first ever mass-produced sequential turbocharger system to be exported from Japan, boosting power to 255 PS or 188 kilowatts or 252 horsepower in 1992, and finally to 280 PS, 206 kilowatts or 276 horsepower by the time production ended in Japan in 2002. For the third generation RX-7, Mazda organized an internal design competition between its 4 design studios in Hiroshima, Yokohama, Irvine, and Europe. The winning design came from their design center in Irvine and was designed by the Taiwanese automotive artist Wu Huangqin, who also worked on the MX-5 Miata, with help from Tam Matano. The interior design, though originated from the Hiroshima design proposal, Mazda's chief designer, Yoichi Sato, then helped take the concept design to its final production form. In Japan, sales were affected by this series' non-compliance with Japanese dimension regulations, and Japanese buyers paid annual taxes for the cars non-compliant with, as the RX-7 was now considered an upper-level luxury sports car due to the increased width dimensions. Mazda also offered 2 smaller offerings, the Yunos Roadster and the Yunos Presso hatchback. The sequential twin turbocharging system, introduced in 1992, was extremely complex and was developed with the aid of Hitachi. It was previously used on the exclusive to Japan Cosmo JC series. The system used two turbochargers, one to provide 10 psi or 0.69 bar of boost from 1800 RPM. The second turbocharger activated in the upper half of the RPM range during full throttle acceleration at 4000 RPM to maintain 10 psi, 0.69 bar until redline. The changeover process occurred at 4500 RPM with a momentary dip in pressure to 8 psi or 0.55 bar and provided semi-linear acceleration from a wide torque curve throughout the entire rev range under normal operation. Under high-speed driving conditions, the changeover process produced a significant increase in power output and forced technical drivers to adjust their driving style to anticipate and mitigate any oversteer during cornering. The standard turbo control system used four control solenoids, four actuators, both a vacuum and pressure chamber, and several feet of preformed vacuum slash pressure hoses, all of which were prone to failure in part due to complexity and the inherent high temperatures of the rotary engine. Information about various trims and models are listed as follows. So you have the Type R, Type RZ, Type RB, A-Spec, EU-Spec, Touring X. As you can see, the A-Spec was the most powerful, followed by the Type R and the EU-Spec. Series 6, 92 through 95. Series 6 was exported throughout the world and sold in larger numbers than in later years. In Japan, Mazda sold the RX-7 through its Affini brand as the Affini RX-7. Models in Japan included the Type S, the base model, Type R, the lightweight sports model, Type RZ, and Type RB A-Spec, and the Touring X, which came with a 4-speed automatic transmission. The RX-7 was sold in 1993 through 1995 in the United States and Canada. The Series 6 was rated at 255 PS, 188 kilowatts, or 252 horsepower, and 294 newton meters of torque, or 217 pound-feet of torque. North American market, and we'll be taking it home from there, right? Good time. Excellent. North American market. At launch, 3 option packages were offered. The unlabeled base model, the Touring, and the R1, renamed R2 in 1994. All cars were only available as a 2-seater, unlike the previous generation, which was a 2+2 configuration in North America. All cars were equipped with the same sequential twin-turbo 13B REW engine. A 5-speed manual transmission was standard, and a 4-speed automatic was available on the base model and Touring package. A driver's side airbag and anti-lock brakes are standard as well. The Touring package included a glass moonroof, fog lights and leather seats, a rear window wiper, and a Bose acoustic wave music system with CD player. The R1, R2, and 94 to 95 model featured upgraded springs, Bilstein shocks, an additional engine oil cooler, and aerodynamics package comprising a front lip and rear wing, suede seats, and Pirelli Z-rated tires. Cruise control was deleted on the R1. The R2 differed from the R1 in that it had slightly softer suspension. In 1994, the interior received a small update to include passenger side airbag, and the PEG, Popular Equipment Group, package was offered. The PEG package featured leather seats, a rear cargo cover, and a power steel sunroof. It did not include the fog lights or Bose stereo of the touring package. An automatic transmission was not available with the PEG. In 1995, the touring package was replaced by the PEP, Popular Equipment Package. The PEP included a rear wing, leather seats, sunroofs, and fog lights, but didn't have the Bose stereo nor the window rear wiper. An estimated 500 RX-7s were produced for the 1995 model year. This would be the final year of the RX-7 production for North America. Now, let's do a quick introduction to carbon fiber. Let me see the differences real quick. See what else came up. Okay, quick introduction. We're going to do both, okay? Carbon fibers, material fibers about 5 to 10 in diameter, composed of carbon. I have to double check that. Carbon fibers or carbon fibers, alternatively CF, graphite fiber or graphite fiber, are fibers about 5 to 10 micrometers, 0.0002 to 0.0039 inches in diameter and composed mostly of carbon atoms. Carbon fibers have several advantages: high stiffness, high tensile strength, high strength to weight ratio, high chemical resistance, high temperature tolerance, and low thermal expansion. These properties have made carbon fiber very popular in aerospace, civil engineering, military, motorsports, and other competition sports. However, they are relatively expensive compared to similar fibers, such as glass fiber, basalt fibers, or plastic fibers. Fabrics made of woven carbon filaments. To produce a carbon fiber, the carbon atoms are bonded together in crystals that are more or less aligned parallel to the fiber's long axes, as the crystal alignment gives the fiber a high strength to volume ratio. In other words, it is strong for its size. Several thousand carbon fibers are bundled together to form a tow, which may be used by itself or woven into a fabric. Carbon fibers are usually combined with other materials to form a composite. For example, when permeated with plastic resin and baked, it forms carbon fiber reinforced polymer, often referred to as carbon fiber, which has a very high strength to weight ratio and is extremely rigid, although somewhat brittle. Carbon fibers are also composited with other materials such as graphite to form reinforced carbon-carbon composites, which have a very high heat tolerance. Carbon fiber reinforced materials are used to make aircraft and spacecraft parts, racing car bodies, golf club shafts, bicycle frames, fishing rods, automobile springs, sailboat masts, and many other components where lightweight and high strength are needed. So remember, we're going to be going over carbon fiber, reinforced polymer, but we're going to go with reinforced carbon-carbon as well. Let's go to reinforced carbon-carbon so we could close it out with the home run, baby. Reinforced carbon-carbon, graphite-based composite material. Carbon fiber reinforced carbon, CFRC, Carbon-carbon, CC, or reinforced carbon-carbon, RCC, is a composite material consisting of carbon fiber, reinforcement in a matrix of graphite. It was developed for the re-entry vehicles of intercontinental ballistic missiles, and it is most widely known as the material for the nose, cone, and wing leading edges of the Space Shuttle orbiter. Carbon brake discs and brake pads have been the standard component of the brake systems of Formula One racing cars since the late 1970s. The first year carbon brakes were seen on a Formula One car was 1976. We have an illustration. Pieces of reinforced carbon-carbon, including a panel removed from the wing of Space Shuttle Atlantis, showing brittle failure of CNC due to foam impact, reproduced in a possible event during Columbia's final launch. Carbon-carbon is well suited to structural applications at high temperatures or where thermal shock resistance and or a low coefficient of thermal expansion is needed. While it is less brittle than many other ceramics, it lacks impact resistance. Space Shuttle Columbia was destroyed during atmospheric re-entry after one of its RCC panels was broken by the impact of a piece of polyurethane foam insulation that broke off from the Space Shuttle's external tank. Now, sorry about that. Let's hit the last home run. Carbon fiber reinforced polymer. Carbon fiber reinforced polymers, American English. Carbon fiber reinforced polymers, Commonwealth English. Carbon fiber reinforced plastics, carbon fiber reinforced thermoplastic, CFRP, CRP, CFRTP, also known as carbon fiber, carbon composite, or just carbon, are extremely strong and light fiber reinforced plastics that contain carbon fibers. CFRPs can be expensive to produce, but are commonly used wherever high strength to weight ratio and stiffness rigidity are required, such as aerospace, superstructures of ships, automotive, civil engineering, sports equipment, and an increasing number of consumer technical applications. Tail of a radio-controlled helicopter made of CRFP. Let me show you guys what it looks like. This is the finished product. These will be cross-beam members for the Jade Phoenix prototype. The binding polymer is often a thermoset resin, such as epoxy, but other thermoset of thermoplastic polymers, such as polyester, vinyl ester, or nylon, are sometimes used. The properties of the final CFRP product can be affected by the type of additives introduced to the binding matrix resin. The most common additive is silica, but other additives such as rubber and carbon nanotubes can be used. Carbon fiber is sometimes referred to as graphite reinforced polymer or graphite fiber reinforced polymer. GFRP is less common as it clashes with glass fiber reinforced polymers. So we're going to do epoxy, we're going to do polyester, we're going to do thermoset, we're going to do silica and carbon nanotubes. And ladies and gentlemen, we have climbed the mountain for today. Our aim is to taste success on a daily basis. We have done that. I want to thank you guys for tuning in. We'll be back on the next one. You guys are my inspiration. Thank you so much for spending all of this quality time with us. And I look forward to meeting all of you guys and going through this semester with all of you guys. Again, I'm still in shock to have, gone to my graduation ceremony for my students. Still emotional, but right back at it. So I have a business meeting to get to. I have a podcast to record. I got a radio show to host. I got another exam finals to give tonight. And I have a few other little creative projects to work on. So just want to say thank you. We'll see you on the next one. Shout out to each and every single one of you out there in the universe that is partaking this time with us. Thank you so much, and God bless. Best teacher in the whole wide world, right here, baby, right here. Peace out.